Greetings, Chem students. This is Mr. Braun, and today we're going to talk about the next unit, and it will start off dealing with kinetics and thermodynamics. Kinetics and thermodynamics. So let's just jump right on in, and here we go. The very first thing we're going to start with is the collision theory. Now, we discussed the collision theory a little bit when we were talking about solutions, all right, and what would help things dissolve, okay? Specifically, what helps a solute dissolve a little bit faster? Well, we talked about collisions. How can we make more collisions, all right? We could stir the solvent. Once we stirred the solvent, that mixed it up quicker. If we get the particles moving faster by stirring, yeah, we get the particles moving faster by increasing the temperature, okay? So we're talking about certain things that can affect the rates of collisions. Now, reaction rate. Let's start off with this, get a definition. It is the number of atoms, ions, or molecules that react in a given time to form products. All right? Atoms, ions, or molecules that react in a given time to form products. Reactions proceed at different rates, okay? Reactions will proceed at different rates. They all don't happen at the same time. Well, let's talk a little bit about this one, sodium. All right. Sodium metal is converted to sodium hydroxide rapidly at room temperature. We watched a video earlier in the year, folks, about the alkali metals. And in that video, we saw the scientists take a knife and cut a chunk of sodium. When he cut that sodium, we could see that it was a very shiny silver color that immediately turned to a dull gray color because it was reacting with the oxygen in the air. It reacted very rapidly. It happened ASAP. As soon as he cut it, the reaction was occurring. Now think about that as opposed to the rusting of iron. Okay? The conversion of iron to iron 3 oxide occurs very much slower. So, with our cars, I'm sure some people have heard of Z-Bark. Okay? That's a protective coating that some manufacturers put on top of the paint. When they do that, it prevents the paint and the coating prevents the metal of your car from coming in contact with the air. Thus, it prevents rusting. However, the lower side, the underside of the car might not have that Z-Bark coating on it. Okay? We definitely don't paint the undersides of the cars, so it might be a little faster rusting on the underside than the painted portion of your car. But nonetheless, that rusting is occurring at a much slower rate. Okay, my car right now is a 2009, and it's got very, very little rust on it. Okay, very, very little rust, probably because the metal hasn't been in contact with the air. All right, so rusting occurs at a much slower rate than what that sodium metal reacting with the air. So reactions take different times. For any reaction involving two or more reactants, the reactant particles must collide. So it's about these collisions that are going to help us determine the rate of the reaction. The more often the particles collide, the faster the reaction takes place. More collisions, faster reactions. Chemical reactions require bonds to break and bonds to be made. So in order for a chemical reaction to occur, we need to break bonds, we need to make bonds. Well, what do we need to break bonds? What do we need to make bonds? We need energy. So the making and the breaking of bonds requires energy. The colliding particles have the energy necessary for bond breaking and bond making. All right. So the particles colliding have the necessary energy to break and make bonds. That's why we're talking about the collision theory. Now, activation energy. Activation energy, let's get a definition first of all. It is the minimum energy that colliding particles must have in order to react. If you remember back when in the lab, we took a piece of magnesium metal. That magnesium metal, we coiled it up, we put it into a crucible. If I would let that magnesium metal set in that crucible, it could sit there for days, it could sit there for weeks, and nothing would ever happen. All right? The reaction would not occur because we did not hit that minimum energy. We didn't hit that minimum energy. What we needed to do is we had to heat the crucible. Once we heated the crucible, we had that minimum amount of energy, and then voila, our magnesium metal reacted with oxygen in the air to form magnesium oxide. But if we didn't have that heat, if we didn't have that minimum energy, it would not have occurred. During a reaction, particles, which are neither reactants nor products, are formed momentarily. Okay? Particles that are neither reactants nor products are formed momentarily. We call this the activated complex. We're going to get another name for that here coming up, I believe, on the next slide. But the activated complex is what we call this momentarily formation of neither reactants nor products. Okay? It is the arrangement of atoms at the peak of the activation energy barrier. The peak of the activation energy barrier, where we have neither reactants nor products. Now, this group of atoms, this activated complex, is only momentarily. It lasts 10 to the minus 13 seconds. So that would be like putting a decimal point and 12 zeros and then a 1. So it's 0.00000, 12 zeros and a 1 seconds. So it is a very, very, very small amount of time. So it is not in this activated complex for very long. This activated complex is very unstable. Okay? It's very unstable. It is just as likely to go back to the reactants as it is to convert into the products. That is why we sometimes call this activated complex the transition state. The reactants are transitioning into the products. Okay? So there we go. Another name for the activated complex is the transition state. Here is a diagram of the energy. What I would like you to do is just go ahead and pause the video and copy this diagram down into your notes. Now let's talk a little bit about this diagram. We are dealing with our axes are energy and the course of the reaction. So the amount of energy and the time that it takes for the reaction to occur. So as I'm looking at this, as I'm seeing this, I can see that my products start right here. Right here are my products. As I am going through, I hit the peak of the activity energy barrier. Right up here at the top, the transition state. We also called that the activated complex. So that's the state right there up at the top of that energy activation energy barrier where we have neither reactants nor products form. 10 to the minus 13 seconds. Very short amount of time. Okay? But let's say if we don't hit that level right there, that reaction's not going to proceed. If I only have enough energy to get me right here, do I have enough energy to convert those further into products? Absolutely not. Not enough energy. So in terms of our magnesium in the crucible, we haven't heated it enough. All right? That's why when we did that experiment, certain people hit that activation energy barrier quicker than other folks did. You know, some of you, it took 5 minutes to hit that barrier, while others of you heated it more slowly. Maybe you had a thicker crucible, something that made it occur at a different rate because it took you longer to hit the amount of activation energy. All right? So we hit the transition state and then we convert over into products. Now let's look at this. Let's look at this. Here are my products. Okay? Here are my reactants. Right? So I have my products, I have the reactants. Which has more energy? Well, obviously, the products are a lot lower than what the reactants is. So we have a change in energy. So this amount of energy right there is how much it has changed between the reactants and the products, right? So we can talk about energy changes that are associated with this. And in this case, we are losing energy. Energy is given off because the products are not as high. Now, is that always the case? Okay. Will there be times when the reactants are lower than products? Absolutely. Absolutely. And we'll talk about that later on in this chapter. All right. Reaction rates. Okay. Reaction rates. How can the reaction rates be affected? Can we affect how fast these reactions occur? Absolutely. Okay, there are several ways in which we can change the rates of reaction. We're going to talk about a few of them today. The first one is the effect of temperature. How does temperature affect the rate of the reaction? Well, if you remember, we can kind of relate this to the solubility we talked about earlier today. All right, when we increased the temperature of the solvent, we made more motion in the particles. When we increase temperatures, particles are moving faster. When we decrease temperature, particles are moving slower. Okay, so as we increase the temperature, particles move faster. If particles are moving faster, what do you think about collisions? That's right, ladies and gentlemen, more collisions. So if we have faster moving particles, we have more collisions. So at higher temperature, the motion of the reactant particles are more chaotic. They have more energy. Thus, we're having more collisions. All right? With more collisions, how does that affect the rate of the reaction? It speeds it up. Therefore, by increasing the temperature of the reaction, we can speed up the reaction. By lowering the temperature, we can slow down the reaction. Let's say we got a scientist who's studying a reaction and he says, whoa, 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 that thing happened entirely too fast. I want to slow it down. What is he going to do? He's going to run that reaction at cooler temperatures. So if he decreases the temperature, we have less movement of the particles. Therefore, we can slow down that reaction. What else? The effect of concentration. We just spent an entire unit talking about solutions, talking about mixtures. Okay, phases and mixtures was the title of the unit. We talked about concentrations. We dealt with words like molarity, molality. The most common one is the molarity, the capital M. And what was the molarity? Well, if you go back and remember the equation, molarity is moles of solute over liters of solution. So how many moles of the solute per liters of the solution? Well, let's think about this. Okay, let's think about this. If I have more moles, do you think I would have more collisions? Let's say if I had 2 moles of a substance, or I had 5 moles. The greater the amount of moles, the more collisions we're going to have. So how does concentration affect? Cramming more particles into a fixed volume increases collisions. When we increase collisions, we increase the rate of reactions. Therefore, increasing the concentration will increase the reaction rate. If I increase the molarity, boom, we're going to have a faster reaction. Next up is going to be the effects of particle size. We were dealing with particle size when we dealt with the solubility of solutions also. And if you remember right, we found out that the smaller particles will dissolve quicker. Okay? The smaller particles will dissolve quicker. So let's look at that in terms of the reaction. The smaller the particle size, the larger the surface area. Okay? So smaller particle size means more surface area. If we have an increase in the surface area, we increase collisions. More surface area, more collisions. How's that affect the collision frequency? That means it's going to have faster. Okay? It's going to have a faster reaction rate. So, if I increase the surface area, I increase the amount of collisions, and I increase the rate of the reaction. So, increasing the particle size, okay? Well, check. Let me go back. Increasing the surface area, decreasing the particle size will increase the reaction rate. Finally, we're going to talk about a catalyst. A catalyst. Well, what is a catalyst? A catalyst is a substance that increases the rate of a reaction. A substance that increases, gonna rain today, folks, increases the rate of a reaction without being used up itself. So, as we're looking at this, we can accomplish this by providing the reactants with a lower pathway of activation energy. So what does the catalyst do? All right, it increases the rate of reaction. How does it do it? By decreasing or lowering the activation energy. Here's a diagram. Go ahead and copy this diagram into your notes. All right, I'm going to move this little thing right here so we can see what's going on there. So go ahead and copy that in your notes, pause the video, and we'll come back here. All right, now that you have it copied down, we have 2 different rates of reactions going on here. The one with the red is without the enzyme. Now, an enzyme is just a biological catalyst, okay? A biological catalyst. So, the enzyme is a catalyst. Without the enzyme, look at the amount of activation energy. It's this amount right here, okay? Here's my amount of activation energy without the enzyme, okay? I'm going to change that. I'm going to do that guy in red since that's a red one. So here is my activation energy without the enzyme, without the catalyst. Here in blue is my reaction with the enzyme. Now I can definitely see that going over the blue hill is not taking as much energy as going over the red hill. All right? So, as I'm looking at this, here's the top, the activation energy peak of my blue hill. Here's the activation energy peak of my red hill. Now, obviously, I don't need as much energy with the blue hill. So that's how the catalyst affects the rate of reaction. It lowers that amount of activation energy, and the reaction proceeds quicker. Okay? The reaction proceeds quicker. We just talked about enzymes. I told you an enzyme is a catalyst that increases the rate of a biological reaction. I'm sure at one time or another you've had liver, okay? You had liver, and the reaction of liver was breaking down the hydrogen peroxide. You did that in biology class at one time or another. So in this bio class, you took the liver and you put the liver into the peroxide, and it broke it down to oxygen gas and water. Well, the enzyme in that biological reaction was something we call catalase. Okay, catalase. So that catalase broke down the hydrogen peroxide faster. Okay, so an enzyme is a biological catalyst. Let's talk about an inhibitor. Okay, an inhibitor is a substance that interferes with a catalyst. An inhibitor works by reacting with the catalyst, thus reducing the amount of catalyst. If we have a lower amount of catalyst, we're going to have a lower rate of reaction. How does that happen? Well, the inhibitor reacts with the catalyst and then causes a slower reaction rate. So if we have a catalyst there, we need to slow down that reaction. A scientist would say, well, I need to add some sort of inhibitor. That inhibitor will then allow my reaction to proceed at a slower rate because it's going to use up some of that catalyst. Okay, ladies and gentlemen, that's all the notes I had today. The key points that we were talking about, the collision theory and reaction rates. And we also discussed 4 points of ideas, 4 ideas that could affect the rates of reactions. Ladies and gentlemen, this is Mr. Braun. Let's investigate.